We are very happy to have Professor Kurt McMullen from the math department, who will be lecturing about some exciting recent developments. I should introduce myself also. I'm Professor Randall. I'm from the physics department, and I'm running this series of Science Center lectures. We're very happy that Kurt McMullen has agreed to give this lecture about some of the developments which some of you perhaps know about from the New Yorker. He claims that he will not talk about the New Yorker at all. Before coming to Harvard, Kurt was a professor at University of California, Berkeley, and at Princeton University, and he was at the Institute for Advanced Study before that. He was educated first at Williams College, I guess that's not first, but an undergraduate, and then he was at Cambridge University, Institut des Études Scientifiques in France, and he was actually a graduate student here at Harvard. He's won numerous awards, including a Fields Medal, a Guggenheim Fellow, an honorary science degree from Williams College, a fellow of the American Academy of Arts and Sciences, and the list does go on. Apparently, he has other interests in addition to mathematics, including semi-professional skiing and filmmaking, and he'll tell you all about those as well. Okay. So please welcome Kurt McMullen.
Well, thank you, Lisa, for that kind introduction. It's a pleasure to be talking at this Science Center lecture series once again. Let me start with a brief recap of the Perelman story, which I think many of you know from the papers. Grigory Perelman was born in 1966 in the Soviet Union, and he now lives in St. Petersburg. In 2002 and 2003, out of the blue, he posted 3 papers to the online mathematical bulletin board known as the Archive, instantly making them accessible around the world. The first paper was 39 pages long, the second was 22 pages long, and the last one was 7 pages long. These papers address a central conceptual problem in 3-dimensional space, which has confounded mathematicians for 100 years. Well, today, 3 years later, a consensus is developing that the work is correct and that the problem is solved. But what is this fundamental problem? Well, luckily, it is a problem in low-dimensional topology, the world of shapes and forms, of geography and maps, of coffee cups and donuts, and loops and knots. My goal tonight, on the eve of this historic breakthrough, is to give you a brief tour of these shapes and forms, to give you a glimpse of the problem that Perelman addressed, and to give you a hint of its remarkable solution. So let's begin with 2 dimensions, with the problem in geography, the paradoxical problem of the shape of the Earth. Now, it appears, as we look around us, that the surface of the Earth has no edge. There's no cliff that just falls off into the emptiness of outer space. On the other hand, the mind reels at the idea that our world should be infinite. How is it possible that our world has no edge, and nevertheless it's finite? Well, the answer, as everybody knows, is that if 2 explorers set off from some point on Earth, say the North Pole, towards 2 very different points on an apparently limitless horizon, they will, in fact, after a mere 10,000 kilometers, find themselves at the equator, and thereafter begin to reconverge, only to meet once more at the South Pole. Our world closes up on a large scale because it is positively curved. In fact, its shape is very close to the shape of a round sphere. So this is our first example of a 2-dimensional manifold. It's a surface, a 2-dimensional shape that has no edge and nevertheless is finite. And this green band, of course, indicates the equator. Okay. Now that's one possible way, one possible model for our world that resolves this paradox. It explains how it can be closed without having an edge. Let's see if I can keep this from rolling off the table. But it's not the only possible answer. So imagine an armchair Magellan many years ago sitting in North America trying to guess the shape of the world without doing much exploration. Well, he might imagine that look, there's seas to the east, seas to the west. Probably those are the same sea. Probably if you head off towards the east, you just return to the west coast of the American continent. And he might similarly reason that he's heard there are frigid regions to the north and the south. Probably those are the same place. And that if you go north, then you simply return where you started from to where you started from the south. Now, if we were to explore such a world, what would we see around us? Well, this is what we would seem to find. As we head north from America, we would just come back to a continent that looks exactly the same. We would see in our world endlessly repeating copies of the American landmass surrounded by a vast ocean. I sometimes think this is what politicians have in mind when they talk about the New World Order. In any case, these are not actually different continents. Of course, we're just coming back to where we started, but by different routes. We're moving around the world in different directions, always coming back home, but it would appear as if there were an endlessly repeating array of North and South American landmasses and nothing else. Now, what would a classroom globe look like in a world like this? Well, instead of looking like this round ball, it would look like this. It would be in the shape of a donut or a two-torus. So this is another example of a two-manifold. It's a closed two-dimensional shape. It's finite. It has no edge. And it's another possible model for the world. Here again is the equator. And here is the single polar area that you can reach either by heading north from the equator or by heading to the south. So that's another conceivable model for the world. That's our armchair Magellan's idea of an alternative model for what the world might look like on a large scale. These two models are radically different. The difference is not a matter of size and shape. No matter how you bend and twist this model, so long as you don't tear it or smush it, you can never turn it into something that looks like a sphere. How can we describe what is a distinguishing feature of this shape that's different from this round shape? Well, let's look at the equator again. The equator is just a loop on the sphere. And we could take the equator, I'm not going to actually do it, but imagine you could roll it slowly towards the North Pole and shrink it to a smaller and smaller loop and then finally shrink it to a point. So on the surface of our sphere, the equator, or indeed any loop, can be shrunk to a single point while keeping it on the surface of the sphere. We say the sphere passes the loop test. So that's one property this model has. It passes the loop test. What about this guy? Well, let's look at the equator on the torus. No matter how you move the equator around, you can't get it off of the torus. It's stuck around this hole. It detects the fact that the torus has a more complicated shape than the sphere. The torus fails the loop test. This loop cannot be shrunk to a point, while this loop can. So that's a way to distinguish these two radically different models for the two-dimensional world. Now here's a picture of some other possible models. We see the familiar two-sphere there and the torus, rendered abstractly in beautiful computer graphics. And then two other examples of surfaces with more holes. This one has 2 holes. This one has 3. The torus only has 1. The sphere, of course, has no holes at all. The number of holes is called the genus of the surface. Of course, this is not really a hole in the surface. It's a hole that the surface is wrapped around as it presents itself in space. The surface itself doesn't have any edges. In particular, it doesn't have any holes. So here's some more examples. And of course, we could make the list go on. We could have genus 4, 5, and 6. Are there any other models we should keep in mind as possible shapes for the world? Are there any other closed two-dimensional surfaces? Are there any other closed two-manifolds? Well, the answer is no. And I think this was probably first appreciated centuries ago in an intuitive way, but the first proof was given by Mobius in 1870, Mobius, the inventor of the Mobius band. And what he showed is that these types of closed surfaces we're considering are in fact determined, their shape is determined by their genus, the number of holes. So if you want to make a list of all of the possible closed two-dimensional manifolds, it's very easy. Here's 0 and 1, and then 2, 3, and 4 go on in the same way, and those are all the possibilities that can ever arise. Now, as you add more holes, the surfaces fail the loop test worse and worse. They have more and more different varieties of loops that can't be undone on them. The only surface that passes the loop test is the sphere. So the fact that this loop, and any loop, can be shrunk to a point characterizes the sphere, the actual model for our world, among all these possible more complicated surfaces. Okay. By the way, here's an interesting exercise in the classification of surfaces. You might go home tonight and rearrange your kitchen drawers, sorting the spatulas and forks and so on according to their genus. And then see if your housemates or your family can guess your system. Okay, now I want to emphasize that this classification is purely topological. It has nothing to do with shape. It just has to do with the overall form of the space. So this is also a sphere from the point of view of a topologist, although it's a more threatening looking one. We say this is a sphere because, in fact, it's just a very distorted object that still could be deformed, so that rather being this blue mass here, it could be just pushed. It doesn't have any holes in it, so its genus is 0, and in fact, it's just a very deformed version of the traditional round sphere. By the way, this shark can also be approximated, as computer animators know very well, by fine networks of grids, fine network of triangles. And so you can imagine that this shark is really a very fine polygon, and thereby an element of ordinary high school geometry. So this says that this kind of geometry, although it's very distorted, should be thought of as being the same as this kind from a topological point of view. They're both spheres. Now, that seems a little strange. This sphere is obviously better than that sphere, because this sphere is round. What about the other shapes? What about the torus? What about a surface with 2 holes in it? Does it also have a best shape? Does it also have a sort of roundest possible version, a version that's, say, as symmetric as possible? Well, it turns out the answer is yes. All surfaces can be modeled on one of 3 types of architecture, one of 3 types of geometry. And the 3 types are shown in this picture. The most familiar type of geometry is, of course, Euclidean geometry. Here you see a network of equilateral triangles in the plane. And that can be used to build the torus, as we'll see shortly, at a surface of genus 1. The next type of geometry I want to draw your attention to is called spherical geometry. Now, these lines that are being drawn on the surface of the sphere are great circles. Of course, they looked curved, but you should think of them as being straight lines. These are the jetways that airlines use to get from one point to another as efficiently as possible. So think of these as being straight. They're the lines that of shortest distance, so long as you're confined to the surface of the sphere. And finally, we see on the right here the third and most versatile kind of geometry that can be used to build surfaces. This is called hyperbolic geometry, whereas this geometry is flat. This one is positively curved. This is the geometry of negative curvature. And it turns out it can be used to build surfaces with 2, 3, 4, or any higher number of handles. Okay, so let me acquaint you with this perhaps unfamiliar geometry a little better. So here's a famous etching of M.C. Escher that should be thought of as a picture of the hyperbolic plane populated by angels and devils. Now, these angels and devils are getting small as you approach the boundary of this picture, but don't think of them as getting small. Think of them as all being the same size. We're surveying an enormous infinite plane, and as the angels and devils get farther and farther away, they get smaller and smaller and smaller. While they're getting smaller and smaller, the numbers of angels and devils are in fact growing exponentially fast. Now, Escher, when he drew this picture, he only drew a few generations of angels and devils. For example, here's one attached to a second, third, fourth, fifth, and then who knows what's going on the boundary. So it goes out about 5 generations. Suppose you wanted to draw this picture out 100 generations. How many angels and devils would you need? Well, on the order of this number, 10 to the 100. Also known as a Google, before Google was a search engine. So there's an enormous amount of space towards the edge of the hyperbolic plane. And it's this explosion of room that makes it such a versatile geometry or architecture for building more complicated surfaces. Okay, now let's go back to Euclidean geometry, a little more familiar. Why is this the appropriate geometry for a surface of genus 1, a torus? Well, if you start with a square, you can neatly join the 2 edges together to make a cylinder. Just wrap it up like this. And now, with a little bit of distortion, you can move the top and the bottom of the cylinder around until they join, and then the result is a torus. Another way to put it is that the torus can be neatly tiled by a network of squares without there being any overlap and with the tiles all fitting together perfectly. So that's the sense in which Euclidean geometry is the best geometry for a surface of genus 1, a torus. Okay, now let's try to do genus 2. Here is a top view of a surface of genus 2. So it has 2 holes in it. The surface is not in either of these areas. The surface comprises this region here, and of course, this is just the top of the surface. There's also a similar shape underneath. This surface can be made out of 8 tiles. There's 1 tile here in blue, 3 others on top. That's 4 on top and also 4 on the bottom. So you can build it by gluing together 8 of these tiles. How many sides do these tiles have? 1, 2, 3, 4, 5. So they're not squares anymore. Now they're pentagons. And if we want them to fit together cleanly, first we need the edges to be straight, and secondly, we want them to have 90-degree angles, like the squares do in the plane, so that you can put 4 together at a vertex. Well, it turns out that such a strange object, that is a right-angled pentagon, is available in hyperbolic geometry. It can be ordered from the hyperbolic plane. And here you see an example of such a right-angled pentagon cleanly tiling the entire hyperbolic plane. So you can take 8 of these and put them together geometrically to build a surface of genus 2. And indeed, if you add enough of these pentagons, you could build a surface of any genus 2 or more than 2. So that's what makes this third type of geometry the most versatile of all. Okay. Now, speaking of architecture, present-day architects are beginning to realize the wonderful potential and versatility of construction with curved surfaces. This is, as you probably know, the Guggenheim Museum in Bilbao by Frank Gehry. We are also ready now to turn to a more modern problem. Let us replace geography with cosmology and try to think not about the shape of the Earth, but about the shape of the universe as a whole. Now, again, when we think about the entire universe, there's a paradox. As far as we know, the universe doesn't have any edge. It's almost unimaginable. How could there be an edge? There would be something beyond it. And yet, again, it seems paradoxical that the universe should also be infinite. How can the universe that we live in be finite and not have an edge? How can a 3-dimensional space be like the 2-dimensional sphere? Well, the simplest answer, the simplest way you can build a universe to have a cosmology that doesn't have an edge and is still finite, already appeared in the year 1300 in Dante's Divine Comedy. So let me remind you how Dante envisioned the world. As you know, the inside of the earth is the underworld of Dante's Inferno, and it's organized into concentric circles of hell, which nest down to the center of the earth where Satan himself resides. But the circles of hell are also mirrored by circles of heaven. And in Dante's cosmology, these heavenly circles are populated by planets, by stars, by ever more divine angels. And just as the circles of hell converge to the center of the earth, the circles of heaven get smaller and smaller and converge to a single divine point called the Empyrean. So the circles of heaven converge just as well as the circles of hell, and the universe as a whole is finite. This model for a closed three-dimensional space is called the three-sphere. It's just a three-dimensional version of this image we have of the planet on which we live. Now, it might seem paradoxical that rockets flying away from Earth in all different directions should ultimately all reconverge and land at this Empyrean, at the ceiling of heaven. But it is no more paradoxical than the fact that travelers that leave from the North Pole ultimately reconverge and land and meet again at the South Pole, no matter what direction they head off into. As Flannery O'Connor put it, in a spherical universe, everything that rises must converge. Now, to achieve this convergence that Dante conceived 600 years before Einstein, one must make the whole universe positively curved, just like the surface of the Earth. We must do Frank Gehry one better and bend not just the titanium skin of the Guggenheim in Bilbao, but we must bend space itself so that it can close up and form a sphere. Well, once again, Dante's model is not the only possibility for a finite universe. It is also possible that we are living in a three-dimensional donut. What would a world like that be? A donut could be made, this kind of three-dimensional world could be made from a cube, and it would be like living in a cube, except when you tried to exit through one of the sides, you just re-enter in the opposite side. If you try to exit from the top, you re-enter on the bottom, and so on. Now, of course, the walls of the cube, the faces of the cube, are not themselves visible. We would not notice when we were passing through the cube. But what we would notice, depending on the scale of the universe, is that our own home planet is repeated infinitely often and periodically around us in every direction. So this is just an outer space version of the map of the many Americas. Of course, we seem to see infinitely many copies of the Earth around us, but they're really the same Earth, and there's just many ways of returning to the same planet, depending on how you travel through this universe. Well, to picture this three-torus, or this donut universe a little better, I want you to imagine a somewhat smaller scale model. Imagine, in fact, that the universe consists of Science Center D, and that it's modeled on this kind of geometry, so that as you try to leave through the exit doors tonight, you find yourselves behind the projection screen. And if you try to dig a hole through the floor, you simply drop through the ceiling. And that if you try to exit through that door there, you simply re-enter through that door here. Well, if that were the case, it would be possible for me to take a rope which starts outside of that door. Of course, outside of that door is the same as the outside of this door. Now I'm going to just tie it to itself. Okay, now we have a loop in our world. Now what happens if I try to straighten this loop out? Well, as I try to pull it from the door over there, it just creates slack here, which comes back in through the other side. So this loop is permanently hooked in our space. There's no way we can shrink it to a point. It's just like this loop here hooked around the two-dimensional torus world. And so this three-dimensional torus world does not satisfy the loop test. It doesn't pass the loop test because here is a loop that cannot be shrunk to a point. It can only be removed by more drastic means. On the other hand, if we go back to Dante's cosmology, it's not hard to see that any loop in Dante's cosmology can be shrunk to a point. Even if you have a loop up in the realm of the moon angels, you can simply pull it towards the center of the Earth, which is like the South Pole. It becomes smaller and smaller and finally shrinks away. So Dante's cosmology, the three-sphere, passes the loop test. The three-dimensional torus does not. Well, now we come to the central point of this presentation, namely the Poincare conjecture. So in 1904, the French mathematician Henri Poincare proposed that, just as for two-dimensional spaces, the only three-dimensional space in which every loop can be shrunk to a point is the three-dimensional sphere. This is the only space that passes the loop test. Another way to say this is that there is no fake three-sphere. Anything that looks like it should be a three-sphere, insofar as passing this loop test, really is a three-sphere. And this is the problem I alluded to at the beginning of this talk. It's the central conceptual problem about three-dimensional space that has challenged mathematicians from 1904 to this day. Now, how could you ever try to prove that something doesn't exist, that there is no fake three-sphere? Well, let me digress and talk about a different problem. This is a problem about coloring maps. It's called the four-color problem. So when you color the countries on a political map, you generally want countries that are adjacent to each other to have different colors, so you can clearly see their boundary. The problem here was to show no matter what map you're trying to color, you only need four colors to make sure that adjacent colors have different hues. Now, most maps, of course, use more than four colors, but the problem is to show that they could always get away with using just four. Okay? Well, this problem was in fact solved by Appel and Hawken in 1976. And for many years, the statement of their result graced the outgoing mail at the University of Illinois in Urbana-Champaign. Four colors suffice for any map. Now, how did they prove this? Well, let me tell you the strategy of their proof. Their proof goes like this. Look, suppose there is a map that genuinely needs five colors. Then there has to be a simplest such map, a map with the fewest number of countries possible, but still needing five colors. Okay, show it to me. Then, by some process, I will find a way to eliminate one of the countries, but keep the property that the map needs five colors. Well, if I can do that, then your map wasn't the simplest, and that's a logical contradiction. So there couldn't have been any map that needed five colors to start with. Well, to make this strategy work, Appel and Hawken had to examine thousands of special cases. Or rather, they had to write a computer program to examine thousands of special cases. And their achievement was both revolutionary and controversial. Controversial because it was probably the first major mathematical result that could not be checked by hand. Now, Wolfgang Hawken is not a geographer. He is a noted three-dimensional topologist. And it is said that this result was just a trial balloon for a brute force approach to the Poincare conjecture. You see, the same strategy can be applied. If there is a fake three-sphere, there is a simplest one. And perhaps by examining maybe not thousands of cases, but trillions, we can show that any simplest one, allegedly simplest one, can be simplified still further, and then logically, there can't be a fake three-sphere at all. Well, luckily, this method of attack has never been carried through because it would shed very little light on why the Poincare conjecture is true, and it wouldn't be very satisfying intellectually. Okay, here's our second approach. It's due to Thurston. Thurston's method, also well known in mathematics, is the following. If you can't solve a problem, change the question. So what he did is he said, look, this is too difficult to prove that there's no fake three-sphere. Let me make a much stronger assertion. And what Thurston asserted was that just as in two dimensions, every three-dimensional space can be built using, this time, one of 8 styles of architecture rather than 3. Now, why is this a better question? Well, it's a much better question because it applies to all three manifolds. Every time you come to me with a three-dimensional space, I can try to see if I can find this underlying architecture. If I can, that lends support to the conjecture. And also, instead of trying to rule out the pathology of a fake three-sphere, we're now trying to show all three-dimensional spaces are well-behaved. At the same time, Thurston's conjecture, the geometrization conjecture, implies the Poincare conjecture. If we could solve this, we would know the Poincare conjecture is true. And the reason is that there is only one architecture available for building a space that passes the loop test. And that is the three-dimensional version of spherical architecture. And the only space you can build with it that passes the loop test is the standard three-dimensional sphere. So if all manifolds are architectural, this tames them in some way. And it implies, in particular, that the Poincare conjecture is true. Now, I don't want to tell you what all of these 8 styles of architecture are, but just as in the case of surfaces, there's one architecture which stands out as being by far the most versatile. And again, it is the architecture of negative curvature. Well, I want to give you at least a glimpse of what that style of architecture looks like, which means I want to give you a glimpse of negatively curved three-dimensional space. And to motivate this glimpse, let's suppose that we wanted to stack a bunch of copies of this 12-sided solid called a dodecahedron. We wanted to stack these neatly together in a box, like cubes. Well, cubes stack neatly, but this guy isn't going to want to stack very neatly with other copies of itself. One reason is that the angles here are all wrong. It would stack much more neatly, for example, if all of the angles were 90 degrees. Well, in fact, a version of this solid where all the angles are 90 degrees is available in hyperbolic geometry. So let's take a look at what we see in this picture here. At first sight, it looks like a traditional construction taking place in three-dimensional space or everywhere around Harvard Yard. You can see constructions that look like this, 3 beams coming together. So it looks perfectly reasonable here. But if you look on a larger scale, you see that 5 of these beams fit together at right angles to form a window. So in fact, although this locally looks like traditional flat Euclidean space, this is an architecture taking place in a world of negative curvature. And in this world, we can make a perfect copy of the 12-sided figure that I mentioned before. You can see it. It's the central chamber in this picture here. And copies of this chamber completely fill space in the same ways as the angels and devils completely filled the plane in Escher's drawing. This is a world which is completely filled by 12-sided apartments, each one with a doorway going directly into the next. Now, one thing I need to tell you about this kind of geometry is, as you can imagine from this picture, it's completely rigid. All of the angles, all of the lengths and the beams and so on are uniquely determined once you say just the topology of how you want the various pieces to fit together. And what Thurston's conjecture says is that every three-dimensional space has behind it a blueprint like this. Every three-dimensional space has a blueprint. Okay. Now, I want to give you some idea of the scope of that conjecture. To do so, let's turn to the theory of knots. So a knot is just a closed loop in three-dimensional space. But you can also think of it as determining a possible shape for the universe. Imagine that you have to live in the black void here, exterior to the knot, and you can never actually touch the knot itself. Or you might think of the knot itself as being like a tubular black hole that you can get very close to, but never actually reach because it's infinitely far away. So since a knot can be used to describe a three-dimensional world, the classification of three-dimensional manifolds is at least as hard as the classification of knots. Well, the classification of knots has a long and difficult history. Lord Kelvin, of absolute zero fame, proposed that long before we had the theory of protons and neutrons and so on, he proposed that atoms are knotted vortices of ether. Don't ask me what ether is. And that the different elements, hydrogen, lithium, carbon, uranium, mercury, correspond to different kinds of knots. Fantastic idea. Maybe hydrogen is just a closed loop, helium is the trefoil knot, and so on. Well, prompted by this suggestion, Tate and Little made a table in 1899 of all of the knots up to 10 crossings. There are 249 altogether, some of which are shown here. I'm not sure if you can see this, but there's the 51st knot with 10th crossings there, and the 150th type with 10 crossings there. What's tricky about making such a table? Why did it take 10 years? This is also a knot with 10 crossings. Can you find it in this table? I mean, the thing is, it might be in that table, but shown from a completely different perspective, and with the loops all moved around and so on, and yet we would still consider it to be the same knot. So the problem in making these tables is that it's very hard to tell when two knots are really the same. They might look very different, but perhaps there's some way we never thought of moving one around so it becomes the other. And in fact, even though it took them 10 years to produce this table, it was wrong. So in 1974, Kenneth Perko, a New York lawyer, noticed an error, that these two knots are in fact the same knot. And so in fact, the original table had 250 knots in it, but we now know it should only have had 249. Well, Thurston proved as support for his geometrization conjecture that every knot has a blueprint. He proved that the geometrization conjecture is true for knot complements. And this result and this viewpoint revolutionized knot theory. Since every knot has a natural architecture, the blueprint for that knot is a signature by which you can tell that this knot is different from another one. And in fact, in 1985, Thurston's graduate student, Jeff Weeks, as part of his Princeton thesis, wrote a program for the little gray Macintosh, some of you may remember, that finds these blueprints. You take your mouse, you draw a knot, you click, and a few seconds later, it determines a canonical blueprint for the knot. It's almost like a reverse kind of paleontology. You give it the soft matter of the knot, and it reconstructs the rigid underlying skeleton. Well, this program easily replaced Perko, Tate, and Little. It immediately identifies the Perko pair as being identical knots, and it quickly can carry out the classification of all knots up to 10 crossings. And in fact, in 1998, Hosta, Thistlethwaite, and Weeks classified all the knots up to 16 crossings. Their paper was entitled The First 1,701,936 Knots. So this classification has now become routine exactly because these wobbly knot-like spaces have a canonical underlying rigid architecture. By the way, Weeks, who is now a MacArthur Fellow, is lately involved in astronomical space shots like the COBE, the Cosmic Background Explorer, and WMAP, the Wilkinson Microwave Anisotropy Probe. And why is he involved in that project? He's trying to determine if our universe passes the loop test. You see, if it were true that in our universe, somehow if we look this way and that way, we're actually looking at the same thing, you would see some unexpected symmetries in the microwave background radiation. Well, despite these successes and many others, Thurston's methods did not settle the Poincare conjecture. In fact, Thurston's methods start with hyperbolic geometry as sort of their main perspective, and they slowly work outwards through the other geometries, and the Poincare conjecture would be the sort of the very last step in Thurston's program. It hasn't quite reached that point. It might, but let me tell you about a program that seems to be even more successful. So the last approach is due to Richard Hamilton, It's called evolution by curvature. I think this is the only real equation I have in this talk. So Hamilton's approach is summarized as a process summarized by this equation above. And the idea is to try to take our unknown or distorted manifold and gradually remold it back into a recognizable shape. Now, what is this Rij sitting on the right-hand side of the equation? This is the Ricci tensor, which is also a central player in Einstein's theory of general relativity, the theory of gravity. It measures part of the curvature of the manifold. And what this equation says is that you should evolve the shape of the manifold with the evolution being guided by the curvature. And the guidance tries to make the manifold look more symmetric. Now, to try to appreciate this approach, one must realize that the classification of three manifolds is, at its root, a combinatorial problem. It's almost like a recreational problem. It's like solving a crossword puzzle. I mean, this is why somebody who's a lawyer in New York could make a contribution to knot theory on a rainy Sunday afternoon. Now, what does Hamilton propose to do? He proposes to solve crossword puzzles using an atom smasher. Now, why is this analogy apt? For two reasons. First, he's using a very powerful tool here that even has some resonance with physics, as an atom smasher does. But what's equally remarkable is that an atom smasher doesn't know anything about Broadway musicals or baseball players or puns. How can it possibly solve a crossword puzzle? In the same way, Hamilton's approach doesn't use any topology. So how can it possibly be used to solve a topological problem like the Poincare conjecture? Well, here's the idea. Here we have an alleged fake three-sphere. It looks sort of like a starfish. It might be some bizarre counterexample to the Poincare conjecture. How can we see if it's a counterexample or not? Well, what we are going to do is we are going to evolve this shape by taking the places where it's curved concavely and pushing them out, and taking the places where the curvature is convex and pushing them in. What happens when we let this shape evolve by that process? You see it very quickly becomes a symmetric round circle. And it's now recognizable as something which is basically a sphere. And so that proves it wasn't a counterexample to the Poincare conjecture. Now, what is miraculous about this process? What's miraculous is that each of these points is moving according to a law that has nothing to do with what the other points are doing. No one is examining the global geometry of the picture to try to make sure things work out in the end. It's as if a million tiny ants working independently could undo a knot in your garden hose. So somehow they're all moving around as independent agents, and yet they cooperate to make the original manifold recognizable. Well, that might have looked a little bit too easy, the starfish example. Let's try this one. So one of the things that's kind of amazing about this process that was proved by Matt Grayson is that, in fact, as the curve evolves, it never crosses itself. It's not at all obvious that that's the case, that it should keep, that these pieces here, which are moving by sort of independent rules, might not run into one another. But in fact, it always works out. Okay, so are you convinced now that there is a proof of the Poincare conjecture? Well, you shouldn't be quite yet. I mean, this was obviously a toy example. It's not even two-dimensional, it's one-dimensional. So maybe this proves the one-dimensional Poincare conjecture. What is the stumbling block? Why wasn't Hamilton's program, which was started almost 25 years ago, why didn't it immediately lead to success? What was the technical difficulty? Well, the main problem which you encounter as soon as you go to higher dimensions is that as the space evolves, it can acquire singularities. So for example, we might be starting out with a space that we're hoping is going to be a sphere, and as its shape is being remolded, this terrible singularity appears here, and then maybe it breaks and it sort of splits into two droplets. And if we try to continue the evolution, after a long time, our original space has fragmented into millions of tiny droplets, each evolving independently. What should we do about this? Well, the first thing we should recognize is that the phenomena of these singularities occurring is not a bad thing. In fact, it's necessary for solving this problem. Remember, we're trying to reconstruct the architecture of this three-dimensional space. It might be that this three-dimensional space is a Gothic cathedral and a Bauhaus apartment building connected by a tunnel. And then maybe the whole thing is melted a little bit, so it's not very recognizable. Now, how can we reconstruct the original pristine pieces? One of the things we have to do in the reconstruction process is pull the manifold into two pieces. Say, look, this piece is Gothic, this piece is Bauhaus. You know, you both go off in your own future evolution and evolve and reconstruct your architecture. So these singularities actually serve a useful process. They break the manifold into pieces that have incompatible architecture, and they're a necessary part of the evolution. On the other hand, the analysis of this physical-like evolution law where singularities can occur is very difficult. Now, it turns out that Perlman has spent most of his life studying what are called Alexandrov spaces. This is something of a backwater in differential geometry, but it's exactly the kind of spaces that arise as limits of good old smooth Riemannian manifolds. It's exactly the kind of singular spaces that might arise during Hamilton's evolution law, during this evolution by curvature. So what did Perlman do? Well, what he did in these three papers is first, he showed that he classified the singularities that can arise, and he showed that they are always, so to speak, undoing tunnels between different styles of architecture. The singularities are all understandable. And when one of these tunnels pinches off, there's a way to continue the process, even though the manifold has become singular. Namely, you just sort of round off the corners. This is called surgery. Now you have two smooth pieces, and you try to continue the evolution. And it's not at all obvious that that process can be continued. It might be that the singularities happen faster and faster and faster, and at some point you just have to throw up your hands and say, stop. But in fact, that doesn't happen. The evolution can be, with surgery, can be continued for all future time, and if you wait long enough, the underlying architecture, in fact, becomes visible. So Perlman's three papers prove that the evolution by curvature process reconstructs the architecture of the underlying manifold. Consequently, the geometrization conjecture is true, and consequently, the Poincare conjecture is true. Now, what does this mean for mathematics? It doesn't quite mean that we have a catalog of all the three-dimensional spaces like we do for two manifolds. It's not easy to write a list of spaces as we did before by just counting the number of holes. But what it means is that all of the possible three-dimensional spaces are represented by rigid geometric objects, that these objects can be ordered from one of 8 reputable architects, and that there are no mysterious spaces like fake three-spheres that are lurking on some sort of black market. So if I can shift the analogy a little, if we think of three manifolds as exotic flora and fauna, it's not that every species of creature that ever walked the earth or lived in the oceans or flew in its skies has been found. But it is as if we know that any new species we ever discover will fit into one of 8 well-understood families. Okay, well, let me close with just a few remarks about the process by which this result was achieved. So first, Giordano called mathematics the music of reason. And I think this is an apt metaphor. If you allow that a great opera can take 100 years to write, with its prelude composed by a Frenchman, then rewritten by a Quaker, with its second act taken over by a windsurfer, and the finale written by a reclusive Russian. So what's remarkable about this achievement is that the end result is not a cacophony. Rather, it is a masterpiece beyond the reach of any single composer. The second point I want to make is that although I've concentrated on just a few individual mathematicians whose names were mentioned here, in fact, a great many working mathematicians contributed to this 100-year enterprise. And especially several leading mathematicians have spent the last few years expanding Perelman's work into detailed and complete proofs. And this is also a very notable contribution to the whole enterprise. And finally, I don't want to leave you with the impression that mathematics is just about trying to prove conjectures, any more than exploration is just about reaching mountain peaks. In fact, mathematics is not just about proving theorems, but it's about finding imaginative and productive ways to think about broad areas of abstract reason. So I hope that by recounting the background of these breakthroughs in 3 dimensions, I've also given you a glimpse of new ways to think about geometry and topology and new ways to imagine surfaces in space.
I was told that entropy plays a role in this proof.
That's right. So what's very important in understanding the behavior of flows is, well, here's one thing that would be a disaster. You're trying to take a space and straighten it out.
I wondered what happens at still higher dimensions.
Yes. So there's many ways of formulating questions in higher dimensions. There is, in fact, a perfect analog of the Poincare conjecture in all dimensions. It comes in a couple of different flavors, but the topological flavor, which is what we emphasize here, was in fact first proved in higher dimensions. This was one of Smale's great insights as he took this famous problem in 3 dimensions and set out to prove it in 6 dimensions instead. And it turned out remarkably to be easier to prove that something that looks like a 6-dimensional sphere really is a 6-dimensional sphere than to prove it in 3 dimensions. So in fact, the heyday of topology was about higher dimensional manifolds, and these low dimensional cases were just sort of left over as some curious contingent facts that depend on odd properties of low dimensions. However, 4 dimensions is, well, the story there is, I remember being in graduate school and they said, everyone's working on the 4-dimensional Poincare conjecture. There's a team in Princeton trying to prove it, a team in San Diego trying to find a counterexample. It's only a question of who will get there first. And in fact, what happened was that it was proved in one flavor, the topological flavor, by Mike Friedman, but it's still open in what's called the smooth category. That is, we want to know if something that looks like it should be a smooth 3-sphere is in fact diffeomorphic. The smooth 4-sphere is in fact diffeomorphic to 1. So in 4 dimensions, just the study of spheres is already still open. On the other hand, one could ask for something more like Thurston's conjecture. Can we classify all 4-dimensional spaces? Do they all have good architectures? And there's 2 answers to this question. First, it's known that there are spaces that have no reasonable architecture. And secondly, it's known that the computational problem of telling whether or not 2 4-manifolds are homeomorphic is unsolvable. So it's harder than knot theory. It has many of the same features of knot theory, as you might say, I start with this knot with 10 crossings. Maybe I have to go through a 100-crossing knot before I can take it back and turn it into some other knot with fewer crossings. In 4 dimensions, there is no algorithm to tell when 2 finitely presented 4-manifolds are homeomorphic to one another. So in some formal sense, the classification problem is unsolvable in higher dimensions.
So I'm going to take the liberty of asking a question. Could you define a sphere?
A sphere. Which kind of sphere?
The spheres that you were discussing in 3 manifolds.
Okay, so this is a 2-sphere.
No, 3-sphere.
A 3-dimensional sphere, okay. So it depends on what you mean by define. So of course, I could write down a mathematical equation that defines a three-sphere, but I think if we want to say what a three-sphere is, we should just visualize a three-dimensional space that is made out of two hemispheres. Now, the hemispheres here are two-dimensional balls. Our three-dimensional space will be the world around us with the center of the Earth, as in Dante's cosmology, plus a sort of upside-down version of the same thing that converges to a single heavenly point, the empyrean. So in other words, I mean, I could, of course, define it by writing an equation, but what I would prefer to do is try to give some feel for what it is really like as a space.
So I didn't mean the totally symmetric case. I meant in
Yes.
general what you're trying to prove the loop conjecture about.
Right, so in the general conjecture, you simply have a closed three-dimensional space, and you know that it passes the loop test, and you want to prove that it's homeomorphic to a three-dimensional sphere. So it means that that it can be remolded so that its shape becomes perfectly round. It's just like the shark.
So how dense was Perlman's work? I mean, I know it expanded from his slightly under 100 pages into 300 plus pages in the Asian Journal of Mathematics. And a lot of work that took 3+ years. So how dense was it originally?
The density factor was 10. So I think, I mean, mathematics is kind of, mathematics is kind of amazing this way. That is, the communication between mathematicians, which is really a very interesting process to watch, can be extremely succinct. That is, it's for somebody who's in the midst of working on a problem, telling them how to surmount a known difficulty can be done very concisely once you know how to surmount it. And so I think what Perlman did was, it was sort of like describing a map to the root of Everest. And then people had to come in and put in static lines and so on, and maybe they found a different route around the Hillary Step, et cetera. But in the end, they were able to follow the landmarks that he left to achieve the result. So it was dense.
Question?
Yes. Your last, or the question a couple of questions ago didn't really give much hope for this, but can you do the band test and either even define your object in the case of an infinite dimensional space?
Well, certainly you can talk about the loop test and all of this kind of topology in an infinite dimensional setting. There's nothing special about finite dimensional. There's nothing even really special about manifolds. But when it comes to trying to classify infinite dimensional manifolds, they tend to be very soft. There's sort of tricks you can play in infinite dimensions. There's so much room that sort of everything becomes rather the same as everything else. So just as already in dimensions 6 and 7 and 8, things became easier, there's even worse catastrophes that simplifies things more grossly in infinite dimensions.
It actually gives you some freedom.
It gives you a lot of freedom, right? So I mean, to do something interesting in infinite dimensions, usually you have to change the rules a little bit.
Because I have a hard time of course, imagining at all how we can do the band around the torus in infinite dimensions. I could kind of understand the sphere, but seeing holes in infinite dimensions is...
Well, remember that you don't have to see the hole. What you need is to see the loop. See, I didn't show you any hole in this three-dimensional space. I just pulled a loop through it.
See how the loop can converge until something. Is that what you're saying? It has actually.
Yes.
It is actually there.
Okay, we have time for 1 or 2 more questions. So, we're in the back.
Was there something unusual about Perlman posting on the web? Well, I mean, was he presumably struggling to get published somewhere else? And is there a chance that if he'd done this 15 years ago, we would still be stuck?
So first, I don't think there was anything unusual about posting on the web. In fact, I think that that's now the way people do it. So most mathematicians, in some way or another, post their latest results on the web. And I think if it had been 15 years ago, there would have been Xerox copies of this manuscript circulating. And it might have taken a few months to reach the people who were most interested in it. But what was unusual about it was that it was the democracy of the web. In other words, he basically took his best ideas and gave them to the entire world without any sort of distinction about who should be allowed to carry them further. And I think this is rather characteristic of mathematicians, in fact. I heard once that people who are working in molecular biology sometimes go through the discarded papers at another lab looking for some sort of hot idea. Whereas in mathematics, if one person would just read our paper, we are overjoyed.
Including Xia also.
Okay, well, I think a lot of people were happy to hear about this. So.